So let's take a look at page 406. We're going to take a look at two more examples or kind of free response-ish type questions that involve this second fundamental theorem of calculus, where we're taking the derivative of an integral at some point. Okay, so we're going to take a look at that. Let capital F be defined by this function, which happens to be an integral, but the graph they give us is the graph of little f. So we have a capital F equation, but a little f graph. Answer some of the questions. Complete the following table for the values of capital F. All right, so in this table, for capital F, we want to figure out if we were to plug in 2 for x, what would we get? How might you want to figure that out? Where would this 2 go? The upper bound. We're going to plug it in to the capital F equation for all the x's, and notice how that would become the upper bound of the integral. So we essentially want to figure out, since this is the f graph, the area under the f graph from 3 to 2. Isn't that kind of switched? Typically we went from 2 to 3. So we got to switch the bounds, meaning got to make the integral the opposite. Bless you. So we want this area, which looks like a trapezoid. But since the area is negative, we know it should be, or since the area is beneath the x-axis, we know it should be negative. So area of a trapezoid, we need 1/2 times the height, which is 1, times the sum of the bases, looks like 4 and 6. So the value of this area would be -5. But since we switched the bounds, it would actually change it to a +5. So there's the capital F of x value. If you were to plug in 2, you would get out 5. Let's try the next one. If we were to plug in 3 for that upper bound, what's the area under the f graph from 3 to 3? 0. Good. Another integral property. Let's check out the next one. We need the area under the f graph from 3 to 5. Okay, those bounds are in order, so we don't have to worry about any switching. We just got to figure out the area of that triangle. So 1/2 times the base, which is 2, times the height, which is 6. We'd get -6, yep. Underneath the x-axis, we need a negative area. Let's see, if we did the next one, we're going to plug in 6, so we need the area from 3 to 6. Bless you. So we're essentially taking the -6 area we just found and adding another little triangle piece to it. Let's see, 1/2 times the base of 1 times the height of 3. So that's a +1.5 area for this little triangle. So if we add that to the -6 that we had previously, looks like we get -4.5. And for the next one, if we plugged in 9, we want the area from 3 all the way out to 9. So, let's see. Maybe I'll color this a different color. We got to take this -4.5 that we have so far, which is the area of the blue pieces, and we got to add a trapezoid, looks like, and then another rectangle. let's see, we have negative 4.5 plus this trapezoid, 1/2, height of 1, sum of bases 3 and 6. Then we got to add the rectangle as well, so 2 times 6. I think we're just going to be left with 12 because the moment we add on that little trapezoid, isn't the blue area beneath the x-axis and then this other big triangle up here the same? Those would cancel each other out. So it looks like we're just left with that rectangle, which would be 12. All right, so to help us figure out that table, we were simply plugging in the values in for x and then analyzing the area underneath that f graph. Let's try the next one. On which intervals is f positive, little f? How'd you know? The graph. Okay, this is the graph of little f. They're basically asking you when is this graph positive, aka above the x-axis. So we'd have from 5 to 10. We'll say because the graph of f is above the x-axis. On which intervals is little f negative? Zero to 5, why? Because the graph of f is below x-axis. Perfect. So those two are kind of simple because we just had to look at the graph. It was the graph of f. They were asking us about f, so we could just analyze it at face value. If we take a look at 4, though, a little different, on which value or on which intervals is capital F increasing? Justify your answer. If we want to analyze capital F increasing, what should we kind of pay close attention to? What do we got to try to figure out? Perhaps the table. I mean, this is only certain values, right? So we know perhaps if we go from 5 to 0 that we're decreasing from 2 to 3, right? But we're not quite sure what's happening at 2.5 because that's not really on there. So a table can give us some idea, but maybe not as accurate as we want to be. If capital F is increasing, shouldn't the derivative of capital F be positive? Isn't that one of our connections? How do you think we can figure out the derivative of capital F? Let's take a look at the top. If we took the derivative of capital F, which is basically the left-hand side of that equation, how do we take the derivative of an integral? Second fundamental theorem of calculus. What would we be left with? Just f of x. Good. We'd plug in the top bound, and then times the derivative of the top bound, which would just be 1. And then we have to subtract, plugging in the bottom bound of 3, but then times the derivative of that bottom bound, which would end up being 0. Remember how that kind of just goes away if you have a numbered bound? If you're taking the derivative of an integral, we're just plugging in the bounds as we go, but don't forget those derivatives. So take a look at this. Notice how this was the graph of f, but if f is equal to capital F prime, this is also the graph of the derivative of capital F. Little interesting there. It's the graph of little f, but also the derivative of capital F. So, if this is the graph of capital F as well, when is that graph positive? 5 to 10, the same interval we had before, right? It's just that we're going to have a different justification here. Okay, 5 to 10 because the graph of capital F prime is above the x-axis or is positive, however you want to phrase it. So we just made a really big connection there. Not only is that the graph of little f, but it's also the graph of a derivative, which means we can analyze that for maxes, mins, increasing, decreasing, all those different characteristics. Let's try on which intervals is capital F decreasing? Bless you. Our justification should be something like because the graph of capital F prime. Notice how they're asking us about capital F, so we should have some type of justification with a capital F. Can we fill in that interval and justification? 0 to 5, because the graph of capital F prime is negative, or you could say below the x-axis. Perfect. Okay. So that graph at the top means two things. It's the graph of little f, but also the graph of the derivative of capital F. Two different things. On which intervals is capital F concave up? Can we somehow relate concavity to the graph of capital F prime? That's what we have up here. What should we be analyzing about that derivative graph to help us analyze concavity? Remember our relationships? Okay, so F double prime is positive. Or, what's F prime doing? Increasing. Good. All right, so since that's the graph of F prime, we should be trying to figure out where is F prime increasing. Can we give our interval? 3 to 7. Because F prime of x is increasing. Let's try the last one. On which intervals is capital F concave down? So in terms of our relationships, the second derivative is negative, but unfortunately they didn't give us the graph of the second derivative, they gave us the graph of the first derivative. So the first derivative is decreasing. Can we analyze that interval? 0 to 3. Perfect. Because capital F prime is decreasing. Perfect. So notice how when we define a function as an integral, we can answer a few different things. We can answer function values, like we did at the table. We can answer increasing and decreasing after we make the connection to the derivative. We can answer concavity, because if we analyze the increasing or decreasing nature of the first derivative, that can tell us concave up or concave down. So by defining a function as an integral, we can relate kind of all three broader functions together, like original function, first derivative function, second derivative function. We're good to go. Let's try one that's very similar. Okay, pictured to the right is the graph of little f, two semicircles and one line segment. Let g be the function defined as the integral of little f, specifically from 0 to x. All right. Find the values of g of 8, g prime of 8, and g double prime of 8. Okay, let's just start with the first one. G of 8. What are we going to do with that 8? plug it in for x, right? In the g equation. Notice how x is the upper bound. So we got to figure out the area under the little f graph from 0 to 8. Let's see, we have a semicircle with radius 2, and then a quarter circle that's underneath the x-axis, so we should subtract it, with radius 4. So we get 2 pi minus 4 pi, so it looks like negative 2 pi. Maybe we'll label this as number 1. Okay. Let's try the second one. G prime of 8. So we got to figure out the derivative of g equation, whatever it is, and then we'll plug in 8 for that x value. So at the top, we want to find the derivative of that integral. We got to utilize the second fundamental theorem of calculus. The derivative of an integral will plug in the top bound times the derivative of the top bound, which would just be 1, minus plugging in the bottom bound times the derivative of the bottom bound, but that's just going to go away because it's 0. So it looks like the derivative of g is the same exact as little f. If we plug in 8 into the derivative, we should be analyzing f of 8. Can we figure out or find that value? Can you tell based off the graph? Well, negative 4, right? If we plug in 8 into the graph of f, which this is, we'll get negative 4. So maybe we'll make note of that. Notice how this statement here, okay, when we found the derivative, not only is this the graph of f, but it's also, aka equal to, the graph of g prime. Kind of similar to the last one. So it's the graph of little f, but also the graph of the derivative of g. Let's try this third value they want us to find. Okay, the second derivative of g. In order to figure out a second derivative, you got to take the derivative of your first derivative. Let's go ahead and reference that in number 2 here. So the second derivative of g is the same as the first derivative of f. We're going to take the derivative across that equation. Bless you.
Thank you.
So if we plug in 8 into the second derivative of g, we got to plug in 8 into the first derivative of f. Can you tell what f prime is at the x value of 8? Good, Dan? 0, right. If this is the graph of f, you're looking at that point and the slope at that point, which would just be 0. You have that minimum. Perfect. Good job. All right, let's check out the next one. On which intervals is the graph of g concave down? Okay, so they're asking us about g now. They're not really asking us about something in terms of f. So if g is concave down, we notice that this graph is representing the derivative of g. So what do we need to analyze on the derivative graph to help us determine concavity? They want us to justify our answer. decreasing. All right, so we'll say because g prime of x is decreasing. That's our justification, and now we have to figure out those intervals. So this was the graph of g prime. Where is that graph decreasing? Two to 8, okay. We kind of got to be careful though. You see how we have that vertical tangent at 4? So you're decreasing here, but the moment you get to 4, you're kind of vertical. And then after 4, you continue to decrease. So I understand the 2 to 8, but we're going to have to be a little bit careful and break it up at 4. That vertical tangent kind of divides it up. Looks good. Let's try the next one. On which intervals is the graph of g increasing? We have the graph of the derivative of g. So what should we be analyzing on that graph? Because g prime is what? What does the derivative need to be or do in order for the original function to be increasing? Be positive. All right, so on the above graph, where is that g prime positive? Looks good. That's where the graph is above the x-axis. Okay, it's the graph of g prime, so it's positive when it's above the x-axis. Are we doing okay so far? These are kind of familiar questions that we've seen before. It's just in terms of representing g as an integral. We're kind of looking at it in a different way. We had to find a derivative first. Let's try the next one. Find the values on the open interval from 0 to 17 at which g has a relative minimum. Justify your answer. If the graph above is the graph of g prime, what does it have to do in order for you to identify a minimum? There we go. Changes negative to positive. So can you find a spot on that graph where it changes negative to positive? You see it?
12.
12. You're negative before, positive after. All right, last but not least, what are the x-coordinates of each point of inflection on the graph of g? What does g prime have to do in order for you to identify a point of inflection? Think about your relationships, yeah.
The graph has to have a slope that equals 0, or it goes from positive, negative, and negative.
All right, so g prime changes positive to negative, or sorry, changes the slope. Let's see, we'll say changes direction. So the slope of that g prime changes positive to negative, aka g prime changes direction. So where on that graph do we change direction? Two. Okay, because we initially are increasing and then we decrease, so we have a direction change at 2. And then we are decreasing until 8, and then afterwards we increase, so there's another directional change. And then, let's see, at 12 we increase, but then we continue to increase afterwards, so that's not a directional change. So we just have 2 and 8, because g prime changes direction. How are we doing? Do we need more practice? You want to try some homework ones together? Let's try it. All right. Yeah. Yes. That's fine. All right, on page 410, let's check out the graph at the top. Let's see, picture to the right is the graph of little f, and they tell us capital F is defined as that function. Find the values of the following. Okay, so capital F of 0. That 0 is an x value for capital F. So if we were to plug that in to the capital F equation, we would get 0 as an upper bound. Do we have to switch the bounds? No, right? They're in order. So we got to figure out the area under the F graph from -6 to 0, which is basically that semicircle and then the triangle. So the semicircle is negative, it's below the x-axis, and the triangle is positive. See, I got -2 pi plus 2. Is that what you guys got? Okay. I think you guys can do 8, right? Very similar question. Let's go ahead and jump down to 9. Find the value of f prime of -2. So let's first figure out the f prime equation, and then we'll plug in -2. So at the top, capital F is the integral. We want to take the derivative of that. So the derivative of an integral, we have that second fundamental theorem of calculus. We're going to plug in the top bound, which would be f of 2x, times the derivative of the top bound, which would be 2. Minus plugging in the bottom bound of -6, but times the derivative of the bottom bound, which would just be 0, so that's going to go away. All right, so there's the first derivative value, or equation. Let's go ahead and plug in -2. So we got to figure out f of -4, and then multiply it by 2. What is f of -4? Can you find it on the graph? Because this is the graph of f. Did you get -2? All right, so -2 times 2 would give us -4. I think you could do 10. Very similar. Let's try 11. So this time they want us to figure out the second derivative of capital F, and then we'll plug in 0. All right. So our first derivative of f we had in number 9. We got to take the derivative of that. Now what's a little different, if you wanted to rearrange it, we could rewrite this with the 2 out front, kind of as a coefficient, instead of being multiplied on the end. So in terms of finding a derivative, we'll keep the 2 as a coefficient, but we may have to use some type of chain rule for the function, because notice how we have an inside piece. So we need the derivative of the outside, which would be f prime, keep the inside, times the derivative of the inside, which would be 2. So if we plug in 0, we'll we'll have 2 f prime of 0 times 2. Can we figure out what f prime of 0 is based off the graph? We want the slope of the graph at that spot. Looks like the slope is 1. So 2 times 1 times 2. We got 4. Alright, let's maybe try 1 or 2 from the bottom graph. So they tell us this is the graph of f, and capital G is defined as that integral. I think we can do 12 and 13, figuring out area. Okay, I want to go ahead and practice the derivative because that's mostly what this section is about anyway. So let's take a look at 14. If you take the derivative of capital G, you got to take the derivative of the integral. Plug in the top bound, we would get f of x times 1, which is the derivative of the top bound. But we don't really have to worry about plugging in the bottom bound because the derivative would eventually be 0 because the bottom bound's a number and it's going to go away. So at this point, what we could do is with this statement, notice how we're saying the derivative of capital G is exactly the same as little f. If this is the graph of f, it is also the graph of capital G, because we just said they were the same. We really couldn't make that connection with the first one, because notice how we said the derivative of capital F was 2 times the f graph of 2x. Okay, this does not say capital F prime equals f of x. So these are not the same in this case, but in the second one they are. Okay, we're telling ourselves they're exactly equal. So if we were to plug in -2, we're essentially trying to find f of -2. Plugging in -2, looks like we get out 2. We'll stop there for a day because the bell's going to ring in a little bit. But try some more homework ones tonight. If you have questions tomorrow, bring them in. Okay, we'll go over them if we have to.